All right, y'all. So today we are starting that very essential skill of writing formulas that you are going to need for the rest of the year for chemistry. I want you to give yourself a little grace as you're getting started, and trust me that I will get you through this. And it is just a little bit of algebra each time. Basically, the highest number you have to think about is like 2 times 3. So you can do this, and I will get you through it. Okay, so some reminders about bonding in general. So when a bond is formed, atoms are either going to lose, gain, or share electrons in order to get a full octet. Okay, so whether that's one atom, giving off 2 electrons and one atom takes those 2, or as we saw with Lewis diagrams, like maybe an atom had 2 to give, but another only atom needed 1, well then 2 of those atoms that only needed 1 came into the picture, right? So it's this idea of losing, gaining, or sharing electrons in order to get that full octet, that happy 8 valence electrons. We are going to start by talking about ionic bonding. And so ionic bonds, as a reminder, that is when electrons are lost and gained. So there are actually ions, hence the word ionic bonding, involved here. And so the total number of electrons lost is always going to equal the total number of electrons gained. And that is going to occur between a cation and an anion. Cations are positively charged ions, and anions are negatively charged ions. So what is nice about our elements is that certain elements are always going to lose 1. Certain elements are always going to lose 2. Certain elements are always going to gain 3. And we can use the periodic table to guide us through that. So if you remember, anything in that first column, let's see, I think mine changed a little bit. There we go. Okay. Everything in this first column ends in something S1, right? Lithium is 2S1. Sodium is 3S1. Potassium is 4S1. They all have 1 electron to lose. Everything in the second column, okay, ends in S2. These all have 2 to lose, right? 2S2, 3S2, 4S2. Come over to chlorine. Chlorine ends in 3S2. 3p5, so it has 7, so it just needs to gain 1 in order to get to 8. All right, and so we talk about that metals are always going to lose electrons and non-metals are always going to gain them. And so that sentence at the top is particularly important to keep in mind as you think through this. So this part up in blue up here, okay, this idea that metals are going to lose electrons, non-metals are going to gain electrons. And so you can see on here how there's this little staircase, and you can see it on the big one on the wall. That staircase is dividing our metals and our non-metals. So all this stuff over here, okay, and that is going to include these friends down here. Those are all going to form cations. They're all going to lose electrons, therefore forming positive charges. Okay, so all of those metals lose electrons and therefore have positive charges. And then on this top part over here, those are all our nonmetals, and the nonmetals are all going to gain electrons, and therefore they will form negative charges, right? Electrons are negatively charged. If you are gaining electrons, then you are going to have a negative charge. So when we're talking about ionic bonding, we're talking about ions participating in these things. What we also can't forget, so we said that it's formed between a cation and an anion, but let's break those terms down a little bit more, right? So cations are anything with a positive charge. So therefore, that's going to be our metals. Our anions are anything with a negative charge. And so we just said our non-metals can do that. But we have something else that we have started to learn that all have negative charges, and those are polyatomic ions. So when we talk about what is participating, it's typically going to be between a metal and a non-metal, or a metal and a polyatomic ion. Those are what we are likely to see. So when we think about those charges, here's a quick little table that just kind of recaps what we just said. What I think is super helpful to do to keep this straight in your mind is if you look across the periodic table, so start here and go across, ignore these down here for me for right now. It goes 1, 2, 3, 4, 3, 2, 1, 0. Okay, and so that's a helpful way to sort of remember it. Again, that was 1, 2, 3, 4, 3, 2, 1, 0. Now you do need to remember that these friends over here are positive, and then that these friends are going to be negative. For our class, we're not actually going to worry too much about this column for right now. Okay, so the reason they're plus or minus 4 is because it's just as easy to lose 4 as it is to gain 4. And then we remember we had the carbon that was magic and blah, blah. Don't worry about that column for right now, but it does help you keep track of moving those things across. Okay, then down here, we have 3 that are highlighted. Okay, right there. And if you were to look at a normal periodic table, that would be silver, cadmium, and zinc. Okay, those 3 are magic because they have set charges. And that was actually on that paper that said other memory work. Silver, zinc, and cadmium. Those are the 3 charges that you do need to memorize. Everything else, right? You can look at the periodic table. First table +1, second column +2. All the way over here, last column -1, whatever. Those 3 you need to memorize, okay? Then notice the rest of these are these white and black ones. We'll get to that later in the lesson. Those are called transition metals. Don't worry about those yet. But again, 1, 2, 3, 4, 3, 2, 1. That is like, you want to keep that in your head as you're trying to do this. I included those polyatomic ions here. One thing to note is that we do have 1 positively charged one. Okay, while all the rest are anions, you do have that 1 cation. Okay, all the rest of them have negative charges and are going to be anions. Okay, so let's get into this. We have heard of things like sodium chloride. That is something that most people have heard of at some point in their lives. That is an ionic compound. So we're going to go over first what happens when you are given the name, and then, given the formula, and then you need to write the name. You'll notice that these notes are large, okay? There's lots of practice involved, lots of exceptions, things like that. We'll get through it, okay? So when you're given the formula, the cation's name does not change. So as a reminder, your cations are typically, let's see if I can, there we go. Your cations are typically this part, and your anions are going to be over here. Okay, so cations and anions. So it says the cation's name doesn't change. So when you're looking at here, beryllium, lithium, sodium, chromium, calcium, cesium, you just name what you see, okay? The nonmetal retains the root of its name and adds the ending IDE. That's what suffix means, an ending. Okay, so the nonmetal, right, that's our portion over here in blue. Nitrogen keeps the root, nitride. Okay, you add that IDE, oxide, fluoride, chloride, sulfide, phosphide, bromide, iodide. Okay, it adds that IDE ending. And that's really all we're going to use for this class. Nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, iodine. That's not many. And again, you just take that part of the name and you add "ide." And so that thing where we always are talking about sodium chloride, this example, sodium, Na, cation, chlorine, our anion, becomes chloride. The polyatomic ion retains its name, meaning if you see SO4, it's sulfate. It doesn't become sulfide. Sulfide is the element sulfur. Okay, so whenever polyatomic ions are involved in these formulas, you just name them like it is, okay? Wherever you spy them, you just name it. Dichromate, cyanide, carbonate, whatever, okay? That's why it's crucial that you know these. So this is what a question would look like. It would say, what is the name for NaCl? And you would want to go through, so in green, I've kind of highlighted like what your thought process needs to be. So it says, what is the name for NaCl? So Na is our cation, and it is sodium. Cl is our anion, and it is chlorine. Okay, so we've got sodium and chlorine being put together to make this formula. The metal keeps its name, great, it just stays as sodium. Okay, and then the non-metal, you take that root of the name, that sort of chlor, okay, and you add IDE. Okay, sodium chloride. Let's look at another one. So Ca, that is our cation. That's calcium, right? Uh-oh. Okay. And then SO4, this is an anion, and if you don't know your polyatomic ions yet, you find SO4 is right here, not to be confused with SO3. SO4, that is sulfate. Okay, so we've got calcium and sulfate coming together. The metal keeps its name, so it is calcium. The non-metal would add IDE, or the polyatomic ion keeps its name. Sulfate is a polyatomic ion, so we simply have calcium sulfate. That's it, okay? You basically are naming what you see for these things. Here's another one, MgF2. So go ahead and type that one in. Right, so just walking it through, Mg is magnesium. F is fluorine, right? We're just naming what we see. Those little 2's and things don't matter yet, okay? Don't worry about them. We're just naming the cation and naming the anion. So our cation keeps its name, magnesium. Fluorine, right? You're going to take the base of that name and add the ending IDE, magnesium fluoride. All right, so ionic compounds, writing the formulas. So this is where it gets harder. The naming isn't so bad, right? You just name what you see. Calcium and fluorine, potassium and sulfate, lithium and bromine, right? You're just naming what's there. It's kind of like a symbols quiz, all right? Where we're writing the formulas, this is where a little bit of math comes in. And again, the math we're talking about is like 2 times 3. So you can do this, maybe even just 1 times 2. All right, so you're gonna write the symbol and the charge for the cation and the anion. So what I mean by that is writing the symbol like Li, okay, if that's our cation, and then its charge. Well, lithium's in that first column, okay, and so anything in that first column is +1. So we would say it's lithium +1. And then your anion, you need to do the same thing. So if it was fluorine, great, you'd write fluorine. It's in the second to last column, so it's -1, F -1. Or a lot of the times those anions are polyatomic ions. So if it said, you know, phosphate, PO4 -3, right? You need to write that whole thing out. So then it says balance the charges to form a neutral compound. Find the least common denominator. So what we are saying there is that the total positive charge must equal the total negative charge. So earlier I talked about, right, how like the number of electrons lost has to be the same as the number of electrons gained. That's the same thing we're saying here, that the total positive charge has to be the same as that total negative charge. So if you have 3 elements with a +1 charge, then that is +3, right? If you have 1 element with a -3 charge, then that is -3. So +3 and -3 cancel out, okay? So that's what we're talking about here, where we're balancing the charges to form a neutral compound. And it's gonna make more sense as we do it, but that's kind of what that's talking about. Your total positive charge must equal your total negative charge. And then at the bottom it says make sure you have the lowest ratio, meaning, you know, if you never see H2O written as H4O2, right? It's simplified, it's H2O, okay? That is what that last piece is saying. So let's walk through an example. Again, one that we have heard of numerous times in our lives, sodium chloride. Okay, so thought process here again is in green, and then kind of you working out is in black. So sodium, right? We know that the symbol for sodium is Na. You find sodium on that periodic table, right? Here it is. It's in that first column, and therefore it has a +1 charge. And so when we list it, it's sodium +1. All right. Chloride came from chlorine, right? So remember, if it's ending in that IDE, it was just a regular non-metal. Your polyatomic ions have their normal names. So sodium chloride was chlorine. The symbol for chlorine is that Cl. When we find chlorine on the periodic table over here, okay, oops, sorry, right here, that column, that second to last column, is -1. And so we would write that charge to be -1. Okay, so then it says how many of each atom is needed to make the compound neutral. So again, the total positive has to equal the total negative. So the charge of sodium is 1, the charge of chlorine is -1. Therefore, when you put them together, they cancel out. And that is why the formula for sodium chloride is simply NaCl. And think back, right? Sodium ends in S1, chlorine ends in S2P5. Sodium has 1 to lose, chlorine has 1 to gain. That's where those ions are coming from. And that is why it is that perfect 1-to-1 ratio of NaCl. So let's look at when they're not the perfect ratio. Sodium oxide. So again, our symbol for sodium is Na. We locate it on the periodic table. It's in the first column, and therefore it has a +1 charge. Oxide is oxygen. We locate oxygen on the periodic table. It's right here. Let's go ahead and just write those charges in here. +1, +2, +3. This was our plus or -4 that we're not really worried about. -3, -2, -1, 0. So oxygen is in that -2 column. Okay, so how many of each atom is needed to make the compound neutral? So right now, if I have 1 sodium, that's a +1 charge. And if I have 1 oxygen, that is a -2 charge. The total electrons lost has to be the same as the total electrons gained. So when we think about this, the total positive charge has to cancel out with the total negative charge. So this is where that least common denominator part comes in. Simply look at 1 times 2. Multiply those charges together. 1 times 2 equals 2. Okay? And so that is telling me that for sodium, in order to get it to equal 2, I need 2 of them. Let's see. There we go. Na2. Oxygen is -2. So in order to get 2 to equal 2, I just multiply it by 1. So that means I need 1 oxygen. Okay, so when you are going through this, those little subscripts are going to tell you how many of each of those ions or those elements that you need. So again, sodium was +1, oxygen was -2. I need to put them together in a way that they are going to cancel each other out. All right, so +1, -2, you put them together, they don't cancel out. So I need 2 sodiums in order to cancel out. And again, think back to those Lewis diagrams. Sodium would have 1 dot on top. Oxygen would have 2 empty spots. And so those sodiums, 1 will fill in 1, and then you bring in another sodium to fill in that other empty spot in the Lewis dot diagram. Okay, and so that is why it is Na2O. Aluminum chloride. All right, so our symbol for aluminum is Al. When we find it on the periodic table, right here, it's in that +3 column. Chloride is chlorine. We find it on the periodic table right here. It's in the -1 column. Therefore, it's Cl with a -1 charge. So when we think about our least common denominator, we have 3 and 1. 3 times 1 is 3. So that is what I need. I need a total of +3 and a total of -3. My aluminum is already at +3. So I only need 1 aluminum. Chlorine is at -1. I need it to be -3. Therefore, I will need 3 chlorines to do it. And so we say Cl3. Aluminum oxide. So these are ones we've used so far. We just used aluminum, so we know that it's +3. And we used oxygen up here, right? So oxygen is -2. Okay, so when we think about the least common denominator here, we have a positive 3 and a negative 2. So this is the hardest math. 3 times 2, okay? 3 times 2 equals 6. So the total electrons lost and gained needs to be 6. So if aluminum is plus 3, I need it to be positive 6. I'm going to need 2 aluminums to do it. Oxygen is minus 2. I need the total negative to be minus 6. So if I have minus 2, I need to multiply it by 3 in order to get 6. That is what we're talking about with least common denominator. All right. Sodium sulfate. Okay, so sodium is Na, and it's in that first column, so it's plus 1. Sulfate is a polyatomic ion, so it's one of the ones that you need to have memorized. Sulfate is SO4 minus 2. So we look at the least common denominator. 1 and 2 is 2. So the total positive charge needs to be plus 2. The total negative charge needs to be negative 2. Therefore, sodium, we're going to need 2 of them because it's plus 1. I need it to be plus 2. Therefore, I need 2. Sulfate is negative 2, so it already equals negative 2. So we simply need 1. So 4. One more from me. Magnesium oxide. All right, so magnesium. Oops. There we go. Magnesium, when we look at the periodic table, it's in that second column. Therefore, it is plus 2. Oxygen, we've used a bunch, is negative 2. So those, while their least common denominator is 2, right? 2, both the number 2 goes into the number 2. All right. Therefore, we actually only need 1. And so this is sometimes where I'll see students do things like Mg2O2. No. All right. This one here, we simply need it to be just one of each because the positive 2 will cancel with that negative 2 and it becomes MgO. So now you're going to take a beat and you're going to do these 6 practice problems. So for the 3 on the left, you are going to submit their names. And for the 3 on the right, you are going to submit their formulas. So go for it. All right, so let's just pop in here real quick. Li is lithium. Cl is chlorine. So it's simply lithium chloride. Ca is calcium. S is sulfur, calcium sulfide. K is potassium. SO4 is sulfate, potassium sulfate. Over here where you're writing the formulas, this is where you need to think through charges. Calcium is plus 2. This is not something you ever have to memorize. You can always look at a periodic table. So the least common denominator is 2. Calcium is already 2, so we only need 1. Fluorine is a 1, so therefore we need 2. Cesium is plus 1. Sulfur is minus 2. Therefore, our least common denominator is going to be 2 again. So cesium, I have 1. I need it to be 2. Therefore, I need 2 of them. Sulfur is 2. Therefore, I only need 1. Magnesium is plus 2. Hydroxide is minus 1. Therefore, their least common denominator is 2. So I only need 1 magnesium and I need 2 hydroxide. Notice the parentheses here. This is a key thing that we'll talk about later, but I wanted to put it in now. If you simply wrote OH2 without parentheses, you're saying 1 oxygen and 2 hydrogens, but that's not what we said out loud when we were thinking it through. We said we need 2 hydroxides. So use those parentheses when you need more than 1 polyatomic. All right. So let's talk about transition metals. I want you to think about this question for a little bit in your notes. And after you've given it a thought, restart the video. All right, so my guess is that as you thought of this, maybe you just wrote FeO, maybe you wrote nothing, maybe you wrote AgS, maybe you wrote AUS. Did you mix up silver and gold? But my hope is that some of you were like, because when you look at the periodic table, remember this section in white and black? Other than those rogue 3 right there, we don't know charges. And so gold, iron, you don't know their charge. So unfortunately, that was super brutal, but I gave you a trick question. So rude. So the answer to this is a big old can't do it, okay? Can't do it. Mean Mr. Wagon. Okay, so when we talk about transition metals, again, it's going to be this little section right here. Other than those rogue, three right there, for the rest of them, you have to tell me what their charge is in their name. So when we were talking about all these beautiful happy metals over here, we could just say magnesium, calcium, potassium, sodium, lithium, whatever. These friends in the middle, they have a little extra to them where we actually need to state what their charge is in their name. You'll be fine. It's a little what I call reverse algebra, which I realize doesn't make a ton of sense. But let's talk about this example right here. So FeO versus Fe2O3, right? So they're both technically iron and oxygen. So let's talk about what the heck do I mean by reverse algebra. And this is our last bit for today, so hang in. All right, so when we talk about iron oxide, like they're both freaking iron oxide. FeO. All right, we don't know the charge of the iron, so I'm going to call it X. Oxygen, we do know the charge of. Oxygen is -2. Remember that for these things, the total positive has to be the same as the total negative. So basically, you're saying X plus -2 has to be 0, right? The total electrons lost has to be the same as the electrons gained. So if 2 electrons were gained, 2 electrons has to be lost. And so this friend is iron 2. Okay. Let's look at the next one. Fe2O3. So now we have 2 irons. So we have 2X that we don't know, plus, oh, come on, pen. We have 3 oxygens at -2, and that has to equal 0. So 2x minus 6 equals 0. 2x equals 6. X equals 3. This friend is iron 3. Oh gosh, sorry. Come back. There we go, sorry. My pen is having a hard time today. But yes, so right here, because we have that 3, we're gonna call this iron. I'm doing this with my finger. My pen just had enough. Maybe that means we should wrap it up. Iron 3, all right? Those Roman numerals are going to tell us our charges. So whenever you see a Roman numeral, that is the charge. You don't have to think it through. It's just there, okay? So let's look at a few of these now. Oops, we're still super zoomed. All right, so here. So for this one here, we have Cu and Cl. So it would be easy to just want to say, you know, copper chloride, right? Because copper is the cation, and chlorine is our anion. But because copper is a transition metal, we have to include its charge. So we go through this math again, this pretend algebra. So this is our X plus the charge of chlorine is -1 equals 0. X equals 1. So when we name this one, it is copper 1 chlorine. And then remember, when we are naming it, the INE becomes IDE, copper 1 chloride. Again, always keeping in mind that that total positive has to be the total negative. All right, here we go. Fe is iron. SO4 is sulfate. So we might want to call it iron sulfate. But ding, 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 transition metal. So we need the charge. We have 1 iron, so that is our X. Plus, remember, this whole thing is sulfate. That doesn't mean 4 sulfates. Sulfate is SO4. Okay, so be very careful there. Sulfate is -2. Therefore, X is 2. So this is iron 2 sulfate. Here's a big one. Okay, so V is vanadium. And O is oxygen. Again, transition metal, we're including that charge. V2 tells me I have 2 vanadiums, so I call it X because I don't know its charge. I have 5 oxygens that have a -2 charge, and it's going to be 0. So 2X equals 10. X equals 5. Vanadium. And then the Roman numeral for 5 is a V. Oxygen becomes oxide. The other way around, you will simply be given the charge of the transition metal in the name. It'll say iron 2, iron 3, chromium 4, vanadium 3, whatever. Okay, it's written in the name. It'll look like that. Okay, so the only thing that you do need to highlight here, though, is silver is always +1. Zinc and cadmium are always +2. Those are those 3 rogue transition metals that you need to know. All the rest have multiple charges. It has to be given to you. There's nothing else we can do about it. So chromium 2 oxide. Chromium is Cr +2. Oxygen has a -2. Least common denominator is 2. CRO. Okay, so these work just like the rest. So I actually want you to go ahead and submit the next 2. So do copper 2 fluoride and the iron 3 sulfide. Submit your answers there. All right, so copper 2 fluoride. Copper is telling us that it is +2. Fluorine is -1. Our least common denominator is 2. Therefore, I only need 1 copper and I need 2 fluorines. Iron 3 sulfide. The Roman numeral is telling me that it is iron +3. Sulfur is -2. So my least common denominator is 6. So in order to get iron to 6, I need 2 of them. And in order to get sulfur to 6, I need 3. And there we go. Big day, but that wraps it up.